It's on.
It's on?
Yeah.
Okay, good. Okay. Right? So what we have here, friends, is, so you see the point. So suppose you had a batsman who was very, very consistent. Right? And you went to see him batting. And your null hypothesis was that this batsman averages around 50 runs every time he goes out to bat. And you have seen him bat 10 times and his score generally around 20 in those 10 matches that you saw. Then you would say that because I have been told it's a very, very consistent batsman, right? Okay? He seems to be a very consistent batsman. He consistently scores only 20 runs. That's what the data seem to show. So it's very unlikely that this batsman actually has a lifetime average score of 50. Because what I've seen is just around 20. And I've been told that he's a very, very consistent batsman. So he doesn't get out early, doesn't outperform a lot. Right? Whatever his average potential is, he keeps on playing around that generally. So therefore it's unlikely that he actually scores 50 runs on an average as a lifetime batsman. Whereas if you're told that, look here, there is a very explosive batsman who's very good, right? But he sometimes gets out quickly, sometimes scores 300s, right? And if you go there and again saw him seems getting out only in the 20s, that will not be so strong an evidence against the null that he scores 50 on an average. Because his batting is a lot more variable. What you see is as cat is capable of taking many more values. So x bar minus mu, therefore that same gap has less evidence against the null if the variance of the observed is larger. So you divide it by sigma by root n, which is the variance of the observed, x bar. Variance of the variability of the empirical observation. Larger the variability of the empirical observation, lesser is its ability to reject the null. So tell me something interesting. What would happen, what would be the impact on a hypothesis test of the sample size? So if you increase your sample size, what impact would that have on your hypothesis testing procedure? You're right. So variability of x bar will go down. So your ability to reject the null will become sharper. You'll have a stronger ability to reject the null. So many times you cannot reject the null hypothesis only because you don't have enough data. Too small n's, if the n is too small, it will generally not give you any ability to reject the null of any null whatsoever. So larger the n would mean that x bar, that the test is sharper. Your ability to reject the null becomes stronger. What happens to sigma square? Larger the population variance, what will be the impact of that on the hypothesis testing procedure? If the population variance increases, how does it impact the testing procedure? And these are true of all types of tests in statistics. So, not necessarily the Z test alone. If sigma, the population variance increases, what happens to the variance of x bar? Variance of x bar? If the population variance increases, what happens to the variance of x bar? What is the variance of x bar? What is the variance of x bar? What is the formula? Population variance upon the sample size. So the same sample size, the population variance increases, what happens to the variance of x bar? Increases. So the variance of x bar increases, x bar minus mu by sigma by root n becomes smaller. So your ability to reject the null goes down. So the larger variance in the population, your ability to reject the null goes down. Larger is the sample size, right? Larger is the sample size, the stronger is your ability to reject the null. So it says that if you are sampling from population, there is a lot of variability, you must have a large sample size. If you are sampling from a population which does not have too much of a variability, you must sample from, you can work with a smaller sample size. If you are working with a population which has a lot of variability, you require a large sample. On the other hand, if the population does not have that much variability, right, then you can work with a smaller sample. You can work with a smaller sample. Like for example, if you were looking at, suppose a sample of kids who were all 3-year-olds. Okay? Suppose you had samples of kids who were all 3-year-olds, and suppose this was a sample of heights, right? And you wanted to test whether on the basis of these sample, can you say that the average height of 3-year-olds in Mumbai is say 2.5 feet? Right? Suppose you wanted to test the null where the average height of a 3-year-old in Mumbai was 2.5 feet. Right? And you are looking at a sample of 3-year-olds. On the other hand, suppose you are looking at a sample of adults in Mumbai and you are trying to test the hypothesis whether the average height of adults in Mumbai is 5 feet 6 inches. Which of the two samples will need a larger, which of the two tests will need a larger sample size? Why? Because the population variability is high. 3-year-old kids can only have a very limited variation in their heights. But adults can have a much larger variability in the population. So the sample size in the second case will have to be larger than the sample size in the first case to be able to get a good test of hypothesis. Yeah? Sure? Right? So you understood this idea? Well enough? Okay. So let me test out again, because this is very important. So let me. So, and this structure is the always the structure of any statistical test that we are going to study is, whenever you want to test, there will be a representative of what we see. There will be something called a hypothesis, what we believe. You will create a gap and divide it by the variability of the observer. That is what allows you to give a test. Yeah? That's what allows you to actually develop a test. So let me give you one more example. Let me give you one more example. So suppose this is a sample this is a sample coming from a normal population with unknown mean mu, yeah, and say variance 16, yeah. Test the null that the population mean is 4. Test the null that the population mean is 4. Test the null that the population mean is 4. How do you do that? First calculate x bar. What is x bar in this case? 4. So we have, then what do you do? First specify what your h naught is. Mu is equal to 4. Yeah? Mu is not equal to 4. Sure? So what will be the z? What is x bar? The next step is to consider z. What z be? Yeah? What is x bar? 4. Sigma by root n. What is sigma? Upon what is root n? Yeah? This is equal to therefore 0. So can you reject the null? You will never be able to reject the null. You will never be able to reject the null. Sure? Okay, so tell me something. What's the problem with the statement seeing is believing? You can never reject it, no? Because when you're saying seeing is believing, you say sample mean is the same as the population mean. So null hypothesis will be mu is equal to the sample mean. But then that's a test you will never able to reject. Right? So seeing is believing is something which Popper would say is not a scientific hypothesis because you can't reject it. Yeah? You can't reject it because if you believe everything that you see, then there is no gap between what you see and what you believe, and therefore you can't use what you see to test what you believe. Yeah? Sure? Okay. So therefore, this. Now suppose I wanted to change this null hypothesis to 5. Can I reject the null hypothesis or do I fail to reject the null hypothesis? What do I have to do now? Mu is equal to 5. Can I reject it or not reject it? Why not reject it? Because yeah, and minus 3 upon 4 lies between minus 1.96 plus 1.9. So I cannot reject. But suppose I now said that my population variance was 4. Not 16, but suppose my population variance was 4. Can I reject it or not reject it? I still cannot reject it. Okay. Now if I said that my population variance was 1, can I reject it or not reject it? When I said my population variance was 4, that number would become 2 by root 3. 2 by 3, right? With 2 by 3 it would be minus 1, minus 3 by 2, so minus 1.5, I still can't reject it. But suppose my population variance became 1. Can I reject it or can I not reject it? I can reject it, right? I can reject it. So it's obviously not that cannot be possible that the hypothesis was true all the while. All that I am saying is when the population variance is smaller, I have much stronger evidence to reject the null. When the population variance is larger, I don't have enough evidence to reject the null because my evidence itself is very variable. So one given piece of evidence cannot be used. Yeah? For example, suppose you have say suppose if you ask me whether I came, suppose somebody comes late to class, right? I ask that person, did you come to class on time yesterday, right? And ask that person, what time did you come to class? So my null hypothesis is that person came to class yesterday, and that person says no, I came at 9:05, right? Okay. Now whether I can actually use that to say that this person did not come on time depends upon how reliable this person's memory is. Suppose that person always exactly remembers the time when, right? Then I would say that yes, that person came 5 minutes late to class. But suppose that person doesn't really generally remember time, right? His reporting of time is maybe 15 minutes here or 15 minutes there. So he would have come at 9, but he is quite likely to say I came at 8:45 to 9:15 anyway. Then that person's reporting of the time is not strong enough evidence for me to reject the null that this person did not come on time. You see the point? Yeah, so that's essentially the idea behind. So that's what you have seen. As the population variance goes down, the sample, your ability to test the null hypothesis improves. So lower the population variance, stronger is your ability to reject the null hypothesis. Larger is the sample size, larger is your ability, stronger is your ability to reject the null hypothesis. Okay, and this is very important when somebody is telling you that I have done a statistical test and failed to reject the null hypothesis. Then the story doesn't stop there. You must ask that person, what is the variability of your population? Was your sample size large enough to be able to reject an hypothesis strongly? Sure, so those kind of questions are very important. So everybody understood the Z test? Sure? 100%? No doubts about this? Okay. So now I am going to bring to you a story. So we are going back to our original. The reason why we did all this was, we wanted to find out what is the distribution of beta hat. Right? We found that beta hat would be normally distributed. Why would it be normally distributed? Because think of beta hat. Beta hat is what? Summation yeah? Sure? So this can be written as, so let me open these brackets, okay? Or yeah? This is okay? Now this part must be equal to 0. So this part goes out. Sure? So what is beta hat? Beta hat is, so this would, if I open this out, this would be yeah? So that formula is nothing but this, x1 minus x bar into y1 upon summation x minus x bar square plus x2 minus x bar upon y2 into summation xi minus x bar square plus so on and so forth. Right? Okay. So it is really, now look at the concept. All the x's are fixed. All the x's are fixed. Right. All the y's are variable. Y is equal to alpha plus beta xi plus ei. What is yi? Yeah? We have assumed that the error term E is a normally distributed random variable. So we are going to say that EI is normally distributed. We know the mean is 0 and the variance is sigma square E. So E is a normally distributed random variable, which means 0, variance sigma square E. Yi is some constant plus Ei. So what will be the distribution of Y? Yi is a normally distributed random variable plus a constant. So what will be the distribution of Y? Normal. It's a normally distributed random variable. So Yi will also be normally distributed. What will be the mean of Yi? What is expectation Yi? Expectation Yi yeah? Alpha plus beta expectation xi plus 0, because expectation ei is 0, xi is constant, Yeah, so expectation xi is constant xi, right? So we know that yi will be normally distributed with mean alpha plus beta xi, and what will be the variability of y around the mean? So let's find. Is this clear? The mean of y will be alpha plus beta xi. So tell me what will be the variance of y? What is the variance of x? Expectation of x minus expectation x whole square. So what will be the variance of y? y minus expectation y whole square. Expectation of y minus expectation y whole square, right? So variance of y will be, yeah, sure. So if I put this into this formula, what will I get? Expectation of, yeah, so alpha plus beta x plus ei, right, minus, yeah, sure. So this part will cancel and this part will cancel. What will I get? Expectation ei square, right? Expectation. What is expectation ei square? Suppose I wanted to find the variance of ei, what would that be? If the expectation of variance of x is expectation of x minus expectation x square, what would be the variance of e? Expectation of e minus expectation e whole square. Expectation e is 0. So here you get expectation e whole square, which is the variance of e. Right. So variance of y is nothing but the variance of e, which is sigma square. Right? So we know that yi is also normally distributed with mean alpha plus beta xi and variance sigma square e. Right? Okay. Now if y is normally distributed, beta hat from this formula is nothing but y1 into a constant plus y2 into a constant plus y3 into a constant plus y4 into a constant up to yn into a constant. Because each of the y's is normally distributed, beta hat will also be normally distributed, because beta hat is nothing but a normally distributed variable into a constant plus another normally distributed variable into a constant plus another normally distributed variable into a constant and so on, and each of, therefore beta hat will also be normally distributed. This property is called the property of linearity. The OLS estimators are said to be linear estimators because they are y1 into something plus y2 into something plus y3 into something up to yn into something, and because of this linearity property and because the error terms are normal, beta hat is also normally distributed. If the error term is not normally distributed, beta hat will not be normally distributed. Because the beta error term is normally distributed, beta hat is normally distributed. Okay? Right? Now, okay, so we know that beta hat is normally distributed. Okay? Okay, if beta hat is normally distributed, then we need to know what is the expected value of beta. What is the expected value of beta hat? Beta, if covariance xn is 0. We did that in class, didn't we? We did expected beta hat is beta, assuming that covariance x is equal to 0. So, assuming covariance x is equal to 0, that's an important assumption we are going to make. And if covariance x is not 0, then everything I am going to do later on falls flat, right? So, you can't really do any of that kind, right? So, if beta hat is now it's equal to beta, okay? And some variance, which I will write as sigma square. The next step then is to find out what is sigma square beta. How to find sigma square beta. Okay? How to find sigma square beta. That we'll do in the next class. Sure? So thank you folks.